Okay, problem 7 is a conical pendulum, right? Not comical, but conical, right? We're saying that as this thing swings around, okay, instead of just swinging back and forth, it's going to go around, and the string is going to sweep out a cone, right? It's going to sweep out a conical shape. Okay, that's my conical pendulum. Alrighty, so as I do this, since I got a conical pendulum with an 80-kilogram bob, that's that mass on the end of the string, it's the pendulum bob, on a 10-meter wire, making an angle of 5 degrees up here with the vertical. Find the horizontal and vertical components of the force exerted by the wire on the pendulum bob and the radial acceleration of the pendulum bob. Okay, so, and there's a little picture there for you, which I'm going to draw my own, of course. All right. Look. Hello, Bob. All right. Shunk. All right. And here's the vertical. Okay. And this is like a side view looking on this. Actually, you know what? This is a rear view. Look, it's I know they drew it that way. Let's say it's going into the page away from me, okay? This is going to be my rear view. That is always the best view for circular motion problems. All right, I shouldn't say always, but oftentimes that's a really good view. Again, you get to see the radial axis. Where is the center of the circle? You're like, center of the circle is like right here, right? The circle this thing's making as it goes around, right? So I'm looking from the side, right from the side, so I'm looking along the plane of its path, right? I just missed. There we go. Okay. Anyways, it goes around and around and around and around. Okay. So when I do my coordinate axes here, isn't it true? This is going to be the radial, and then this is going to be the z. Okay. And I'm looking along the tangential axis as it goes away from me, as it's swinging around. Okay. So this is, I'm going to call these ways, I'm going to call up, and I'm going to call toward the center of the circle positive. And let's do our force diagram. There'll be ranged forces, gravitational force. Contact force is the only thing touching the pendulum bob is this wire. It is being stressed, and so there is a tension. I drew that probably a little too long, but what are you going to do? Okay, so there's a tension force pulling along the wire. You know that we're going to break forces into components along axes. Radial, z. Okay, they told us that the angle that this wire makes with vertical here, that theta is 5 degrees. That's the same as this theta, 5 degrees, angle with the vertical the wire makes, right? So I could call this component here, this is adjacent to the angles. This is t cosine theta, and this is t sine theta, right? All right, we want to find the horizontal and vertical components of the force exerted by the wire on the pendulum. So we want to find the horizontal and vertical components of the tension. You say, how am I going to find the components of the tension? Well, when in doubt, F equals ma, right? So we're going to do sigma F equals ma. And you say, now we've got 2 coordinate axes to work with here. We're going to start with the z, I think, this time. I know we're always going to do the radial, though, in a circular motion problem. So we're going to come back to that, though. And so if I did this, I would be forces up minus forces down. So that'll be t cosine theta minus mg equals. Now, am I accelerating up and down? Now, remember, from the side view, it's just going around and around and around. It's not, its speed up and down is 0. And it's still 0, and it's still 0. It's just going around a circle like this. So this is going to be 0. We're not accelerating up and down at all. However, we do have an acceleration toward the center to make us turn, right, as it whips around. And so in the radial axis, I am definitely going to have I'm going to have that centripetal acceleration. It's always got to be forces in minus forces out. The only force in that axis is t sine theta. So I'll have that t sine theta is mass times centripetal acceleration, which, let's see. They want me to find the component, and they want the radial acceleration. I'm just going to leave that in terms of AC, because this acceleration here, this is the acceleration we're going to try to solve for. I'm not going to break it down to v squared over r, because they don't tell me v. I'm going to leave it that way for right now. Okay, maybe it's cheating for me to spot that, but I'm going to leave that like that. Okay, so come over here. They want the components. They want us to solve for they say the horizontal and vertical components. They want us to solve for how big is this guy? how big is t cosine theta? You say, well, that's just going to be equal to mg. Do we know the mass of the bob? Yes, we do. They told us it was an 80 kilogram bob. Right? That guy is 80 kilograms. And so I can rearrange this. I can say, hey, look, that t cosine theta, that's that radial component, that horizontal component, that's mg, and that's going to be 80 times 9.8. You say 80 times 9.8, that would be 720 plus 64, so it'd be 784 newtons. Okay, is t cosine theta. That is what we were trying to find. Okay, that is the horizontal component. I'm sorry, the vertical component. That's the vertical component that's balancing out mg, because we're not accelerating up and down. Those have to balance. Okay, now that I know this, can I solve for the radial component? Well, the radial component, I don't know about this acceleration yet, right? But they told me theta. I know that theta is 5 degrees. And so if I know the total, this whole thing is 784, and this is cosine of 5, I can find t. And once I have t, I can plug it in here times the sine of 5 degrees, and I'd have that component. Aha, you say. Am I going to do it that way? Sure, I'll do it that way. And so rearranging this, I could solve that t is 784 over the cosine of 5, right? Okay, and I get that tension is 786.99. Let's just round that to 787. I know, being sloppy. And now I can take that and I can put it in here, and I know that this is 5 degrees, and I can find this whole thing, which is the vertical component, the horizontal component, I mean. And find the horizontal component, the radial component. And so that's going to be 787 times the sine of 5. Okay, so just take that answer in my calculator times the sine of 5 degrees, and I get that is 68.6 newtons. And so that all right. Hey, we got that. So we have that other. This is that horizontal component of the tension. Okay, so those were the two things they wanted us to solve for in the first part of the problem. Now they would like us to find the radial acceleration of the bob. And so you say, okay, well, the radial acceleration, that's AC. And you say, okay, so 68.6, that is mass times AC. If I can just divide through by the mass, we know the mass is 80 kilograms. So 68.6 divided by 80 is going to be that centripetal acceleration. And so you say 68.6, still in my calculator, divided by 80, and you get 0.8574, let's just say 0.857 meters per second squared is that centripetal acceleration, the end. Ta-da! And that is problem 7.